Ready for a mind-bending journey? We're taking a deep dive into Stephen Hawking's A Brief History of Time. This book tackles some of the biggest questions we have about, well, everything.
It's incredible how Hawking takes these really complex ideas from cosmology, space and time and black holes, and makes them understandable, even engaging.
It's true. He doesn't dumb it down, but he finds a way to make you think about the universe in ways you never considered before.
Absolutely. He starts really effectively with how our understanding of the universe has changed over time. Like, remember back when people thought Earth was the center of it all?
Oh, yeah, like we were the most important thing in existence, kind of a big ego boost, until you realize that's totally not the case.
Right. And he talks about that shift from an Earth-centered model to realizing we're just a small part of something much, much bigger.
Talk about humbling. So, how did we get from thinking Earth was the center to realizing, oh, wait, the universe doesn't actually revolve around us?
Well, it started with those early astronomers, even with pretty limited tools. They were looking up, making observations, and starting to ask some big questions like, what is out there? How does it all work?
And we should be thankful for the folks who challenged the accepted views back then. Imagine having the guts to be like Copernicus or Galileo saying, hey, everyone, I think you've got it all wrong.
Right. Talk about going against the grain. But those guys, they took those early observations and basically flipped the script. It wasn't the sun going around the Earth. It was the other way around.
Yeah.
A complete game changer.
Can you imagine the uproar? But that shift to a sun-centered model, that was huge. It opened up a universe of possibilities, literally.
Absolutely. And it led to an even bigger realization that the universe isn't static, it's expanding.
Okay, hold on. The universe is expanding. How did they figure that out?
Think of it like dots on a balloon. As you inflate the balloon, those dots move farther and farther apart.
Yeah,
Right?
I can picture that.
Well, Edwin Hubble, he observed that distant galaxies are moving away from us, just like those dots. And get this, the farther away the galaxy, the faster it's moving. That observation, that was a big clue that led to the Big Bang Theory.
Okay, so the universe isn't just sitting still, it's constantly growing. But what is it expanding into? Like, what's on the other side of that balloon?
That's where our normal, everyday ideas about space and time, they kind of break down. Hawking wants us to think beyond our usual up, down, left, right, forward, backward. He introduces this really mind-bending idea of space-time.
Okay, I'm game. Tell me more about this space-time. Adding another dimension to my life, are we?
Right. Imagine a fabric made of space and time woven together.
Yeah.
That's space-time. It's not just about where something is, but when it is all wrapped up in one.
Okay, so it's not just where, but when. It's a lot to get my head around.
It is. And that's where Einstein's theory of general relativity comes in. This theory says that this fabric of space-time is not flat, it can be warped.
Warped, like bent out of shape.
Exactly. Picture a bowling ball on a trampoline. It creates a dip, right? Well, massive objects like planets and stars, they do the same thing to space-time. They warp it. And that warping, that's what we experience as gravity.
So you're saying gravity isn't a force pulling things together, it's actually the shape of space-time itself. Whoa! That is wild.
It's one of the most mind-blowing insights in physics. And it gets even more wild when you start thinking about what happens when really, really massive objects warp space-time.
Okay, now you've got me hooked. Let's talk about those massive objects. What happens then? So we were talking about how gravity warps space-time. But what about the universe as a whole? Does that warping play into the whole expanding thing?
That's a great question. It's like, picture that balloon again. When you blow more air into it, it's not just the dots moving apart. The balloon itself, the fabric of it, is stretching. That's basically what's happening in the universe. Space-time itself is expanding and carrying those galaxies along with it.
So it's not that galaxies are flying away from each other. It's more like the space between them is stretching like, I don't know, like cosmic taffy or something.
Exactly. And that stretching, that expansion, it has some really, really mind-boggling effects. It affects everything, even time itself.
Hold on, are we talking time travel here?
We might be.
Okay, now we're getting to the good stuff.
Hawking actually explores this idea of time travel in the book.
Yeah.
One way he talks about it is through something called wormholes.
Wormholes, like those tunnels from science fiction,
Oh,
right?
yeah.
Shortcuts through time and space.
You got it. Imagine if you folded a piece of paper in half and then poked a hole through it. That hole would be a very simplified way to think about a wormhole. It connects two distant points in space-time.
So you're saying theoretically I could hop in a wormhole and pop out in a totally different time, like a cosmic time machine. Where do I sign up?
Well, hold your horses. While wormholes are theoretically possible, based on Einstein's equations, There are some pretty big buts.
Okay, like what? Let's hear these buts.
Well, first off, we've never actually seen a wormhole.
So they're like unicorns, these wormholes. Pretty to think about, but nobody's ever actually found one.
Kind of. They're predicted by the math, but finding one, observing one directly, that's a whole other challenge.
Okay, so they're elusive. But let's say, just for fun, we find one. What's stopping us from jumping in and going for a ride?
Well, for one, the physics of wormholes is incredibly complex, and they're probably incredibly unstable too. Hawking actually pointed out that even if we could create a wormhole, it might just collapse as soon as something tried to enter it.
So maybe not the best mode of transportation, more like a one-way ticket to oblivion.
Potentially. And then you've got the paradoxes inherent in time travel.
Like, what if you went back in time and accidentally prevented your own birth? Isn't there a movie about that?
Exactly. It's the classic grandfather paradox.
Yeah.
These paradoxes, they suggest that even if time travel is possible, there might be some fundamental rules, some cosmic laws we don't understand yet that prevent those kinds of contradictions.
So maybe time travel isn't as simple as punching in a date and hitting go. But even without time travel, the universe is a pretty wild place. Hawking also goes into black holes, right? Those are every bit as mind-boggling as wormholes, maybe even a little scarier.
Absolutely. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They're like the ultimate cosmic vacuum cleaners.
And they form when really massive stars collapse. Yeah.
Exactly. When a massive star runs out of fuel, gravity takes over and it collapses in on itself, crushing down to an infinitely dense point called a singularity.
And that singularity is surrounded by the event horizon, right? The point of no return. You cross that line, you're not coming back.
Right. Once you crank the event horizon, gravity's pull is so strong that nothing, not even light, can escape.
I'm getting nervous just thinking about it. But Hawking's research actually brought some pretty surprising twists to this whole black hole story, didn't it?
It did.
I thought black holes were just these giant cosmic vacuum cleaners sucking up everything in sight. What else could they possibly be doing?
Now, that was the prevailing idea for a long time. But Hawking proposed something revolutionary. Black holes might not be so black after all.
Hold on, wait a minute. How can a black hole not be black? That's like saying the ocean isn't wet.
It does sound a little counterintuitive, right? But stick with me. Hawking showed that black holes could actually emit a type of radiation due to some weird quantum stuff happening near the event horizon. We call it Hawking radiation.
Okay, back up. Quantum stuff. So we're talking about the world of the very, very small to explain something incredibly massive.
Exactly. It's a bit complicated, but basically, pairs of particles are constantly popping in and out of existence near the event horizon. Sometimes one particle falls into the black hole and the other escapes. That escaping particle, that's Hawking radiation.
So the black hole is kind of leaking, like it's slowly evaporating, releasing particles back into the universe.
In a way, yes. But this evaporation is incredibly slow,
Yeah.
especially for large black holes. We're talking timescales way longer than the current age of the universe.
Okay, so those monsters aren't going to be disappearing anytime soon. That's a relief. But if black holes are leaking these particles, what happens to all the stuff that falls into them? Where does it go?
That's the million-dollar question. It leads to one of the biggest mysteries in physics, the information paradox.
Right.
Everything that falls into a black hole carries information, right? Information about what it's made of, how it's structured.
Makes sense. So what happens to that information if the black hole evaporates?
That's the paradox.
Yeah.
If the information is truly gone, it violates some very fundamental laws of physics. But if it escapes, how does it do that? And what does that tell us about the nature of information itself?
Okay, now my head is truly spinning. We've got expanding space-time, wormholes, black holes that maybe aren't so black after all. It's a lot.
It's a lot to wrap your head around. But that's the beauty of exploring these ideas with Stephen Hawking. He makes you confront the boundaries of what we know and forces you to consider possibilities that seem, well, kind of bizarre.
So we've got all these mind-blowing concepts floating around: black holes, leaking information, the fabric of space-time itself stretching and expanding. It really makes you wonder what else we might have gotten wrong about the universe.
You know, that's really at the heart of what Hawking challenges us to do, to question our assumptions, even about things as fundamental as time itself.
Okay, time. I think we all kind of take that for granted, right? It just marches on, always moving forward. What's there to question?
Well, we tend to experience time in a linear way, past, present, future. But Hawking asks, what if, at the very beginning of the universe, time behaved differently?
Differently. You mean like going backwards? Or sideways? Time loops, maybe?
Think about it this way. At the singularity, the very, very beginning of the Big Bang, all of our current laws of physics, they just kind of break down.
So it's like a cosmic free-for-all. Anything goes.
In a way, yeah, some theories suggest that at the singularity, time, as we know it, might not have even existed. It could have been all bound up with the other dimensions in a way we can't even really imagine.
Okay, my brain is officially fried. So you're saying there might be something beyond time itself.
It's a truly mind-blowing concept. It really forces us to expand our whole definition of reality. And it's just one example of the really profound questions that Hawking tackled in his work.
It's humbling, isn't it? It makes you realize how much we still don't know about the universe, about our place in all of it.
Absolutely. But it's also incredibly exciting, don't you think? Hawking's work is a testament to human curiosity, to our drive to explore the unknown, even if it bends our minds a little bit, or a lot, along the way.
He definitely left behind an incredible legacy. He opened our minds to the wonders of the universe, inspired people to keep asking those big, fundamental questions, and to not be afraid to challenge what we think we know.
And to remember that even when faced with the vastness of the cosmos, our desire to understand, to unlock these mysteries, that's what makes us human.
Well said. As we wrap up our deep dive into a brief history of time, I'm definitely left with a sense of awe, maybe even a touch of vertigo.
I know what you mean. It's like stepping off a cliff and realizing the universe is still unfolding beneath you.
And that, my friend, is a feeling we should all hold on to. The universe is full of wonder, and we're really just starting to scratch the surface of its secrets. So keep looking up at the stars, never stop asking what if, and who knows what incredible discoveries await us in this vast expanse of time and space. This is The Deep Dive, signing off.